Okay, question 14. We have got a circuit designed for a student to monitor the temperature change. We've got a 9-volt battery connected in series with a 0.25 kilo ohm resistor, and in parallel with this arrangement here, a resistor R and a thermistor. So this is a parallel section and this is a series section. This is in parallel with, so this here is in series with this, and these two are parallel to one another. Now, I've added readings here, but it'll become more apparent why I've added those in as we've gone through the question. So, supply has a negligible internal resistance, and the thermistor has a resistance of 750 ohms. So, what I've done is I've popped that there, 750 ohms at room temperature. Okay, so the student wants the output potential difference, PD, at room temperature to be 5 volts. So when this is 750 ohms, they want this output PD to be a 5 volts. Straight away, as soon as I wrote down 5 volts here, I know that's 9 volts there. So that means that the PD across the other resistor is 4 volts because this is parallel. So if it's 5 volts across the 750 ohms, then it's 5 volts across that. So that's 5 volts across these two. And that is 9 volts, so that we know that 5 minus 9 minus 5, 4 volts. 4 volts goes here. And that will help later on. The 0.25 kilo ohm resistor is made up of 50 turns of wire. Okay, so it's wrapped around 50 times on a non-conducting cylinder of diameter 8 millimeters. So the diameter of this cylinder where this wire is wrapped around is 8 millimeters. Now, the resistivity is given to you here. It says determine the cross-sectional area of the wire that has been used for the resistor. So we know resistivity is given. So try to find a formula that links resistivity and cross-sectional area, which is this here. R equals rho L over A. And we want to find the cross-sectional area, which is rho L over R. Okay, so we want to find the cross-section area, which is the cross-section area of the wire. Okay, and now if many of you are using pi r squared here, which is the cross-section area of this cylinder, non-conducting cylinder. Okay, so that's not what we were looking for. So many of you have gone down the route of going on A equals pi r squared, and you use the diameter of 8 millimeters. You've actually worked out the cross-sectional area of that non-conducting cylinder where those wires are wrapped around. Okay, so that doesn't give you the cross-section area of the wire that's wrapped around. We want to know what that is, and unfortunately, this question, we can't use pi r squared using d as the 8 millimeters. But so what's the significance of that? So when we want to work out the cross-section area using resistivity, length, and resistance, we can use that to find out the length. So we know 1 turn is when the wire is wrapped around the cylinder once, and that's the circumference of the cylinder, which is pi times diameter. Okay, and because it's wrapped around 50 times, it will be pi times diameter times by 50, and that will be the length of this wire. So 1 turn, the length of the wire will be pi times diameter. For 50 turns, the length of the wire will be 50 times pi times by 8 um, times by 10 to the minus 3. So that's pi times diameter. And then times that by 50. That will give us the length of the wire. We'll have the length of the wire. We'll have the resistivity. And we have the resistance. So therefore, we can work out the cross-section area, put everything in, and that's your second mark, and give you an area, cross-section area of 2.11 times 10 to the minus 9 meters squared. And that is the cross-section area of the actual wire. So this is the only way to do it. And for those of you who went down the route of using A equals pi r squared, you haven't got the radius of the wire or the diameter of the wire. You've got this diameter of this conducting cylinder where the wire is wrapped around. So easy mistake to make, but paying close attention to the details within the question. B, so the student selects a resistor of 0.36 watts. So that means that the maximum power dissipation that the resistor could have is 0.36 watts for the 250 kilo ohm resistor. So you got power and resistance. So what I've done is I've done two calculations, and both calculations will get you to the same conclusion. So when I put that 4 volts here before, now when this circuit's operating the way it should, and it said that we want this output voltage to be 5 volts, that means that that resistor that we've just started to discuss has 4 volts around it. So that we've got the voltage, we've got the resistance, so we know that the amount of power of this resistor when it's working the way it should be in this circuit. And that's the calculation I've done to begin with. So the power required for the circuit to operate in the conditions that we set in this question will be 4 volts squared. So power is V squared over R, 4 squared over 250, which is the 250 kilo ohms, 250 resistance, 4 volts, which we've discussed here. Okay, that's when we've got our conditions set, and we see that the power dissipation at the resistor is 0.064 watts. That's the amount of joules per second that's been dissipated in the resistor. So it doesn't exceed the 0.36 watts, so it's suitable. It's only when it exceeds the 0.36 watts that's when it's not suitable. So we require this much, but it's significantly less than 0.36 watts. Okay. Alternatively, you can find out what the voltage here, what the potential difference would be needed across the resistor, what PD would we need across here for a 0.36 watt power dissipation. So all I've done is I've rearranged this equation to get V equals. So V equals the square root of power times by resistance. So just rearrange this. And I find that 0.36 watts multiplied by 250 or rooted, the potential difference across this resistor when this much power is dissipated is 9.49 volts. So that's when it's at the maximum amount of joules per second that can go through that resistor. Now we know that the battery is supplying 9 volts, and we've just said that this can handle more than 9 and just over 9 volts. So therefore it's suitable. So you could have gone down this route of saying that this is how much we need, which is significantly less than 0.36 watts, or we can say that using this, the voltage that the maximum voltage around it that it could have is 9.49, which is much greater than the battery voltage. Sorry, that should be the other way around. Okay, so it's never going to get there. So it's never going to go beyond the maximum power dissipation of that particular resistor. Part C, it says determine the value of R that the student should select. Give your answer. So we want to find out what the value of R the student should select. So we've kind of put the conditions in, remember, as we went through the question. So we know that the resistance has to be 750 across the thermistor, and we need a 5 volt power output. So that means 4 volts goes there, and 0.25 volt kilo ohm goes there. So now I know that 5 volts goes across the 750 ohms. I know the 5 volt goes over R as well because they are in parallel. Now there are a few ways to do this question. What I found was the easiest way was ratios. So I know that the voltage between this section and this section is 4 volts to 5 volts. So the resistance for this section and this section should follow the same ratio. So if that's 250 ohms, then that should be 1.25 times greater than that. And that's 312.5 ohms. And I've done the calculation here. So the voltage is 4 to 5. Where you have 4 volts, that's a 250 ohm resistor. And it's the same ratio for the resistances. So I've done the calculation to find out what the value of this resistance should be, and it's 1.25 times bigger to go from there to there. It's times by 1.25. So from going from there to there, we also times by 1.25, and that gives us a 312.5 ohms. So what's that mean? That means that this entire section here where the 5 volts is around, that entire resistance, overall resistance, should be 312.5 ohms. But we haven't been asked for that. We have been asked for the resistance inside that parallel arrangement. So we know that this is resistances in parallel. So we've got two components, a 1 over RT plus 1 over R1 plus 1 over R2. So that's 1 over 312.5, which we've just calculated, which is the total resistance of that parallel section, equals 1 over 750 plus 1 over R, and that's 1 over 750 and 1 over R. And we've rearranged it. So I've moved the 1 over 70 across to this side, and then flipped it, put it in the calculator, and I've got a resistance of 540 ohms. So that was one technique to get to the value of resistance. Another technique, which is what some students used, was we know that this is 5 volts, so therefore the voltage across this section here with 4 volts. With the resistance and voltage, we can work out current. So we know the current in this section here. But we know that the current splits. Some current goes this way, some current goes that way. So the current that we've calculated splits across these two. But if we look carefully, we know the voltage across the thermistor, but we also know the resistance across the thermistor. So we can work out the current here as well. Knowing the current here, using resistance equals voltage over current rearranged, we can work that. And knowing the current here using the same technique, we can then find the current that we should get across the resistance here. Okay, so we know that that will be the current here minus the current here will give us the current there. We know now the current through here. We know the voltage is 5 volts, and with the voltage and the current, we can work out the resistance here. So the first step, find the current here. Second step, find the current here using resistance equal voltage over current, and then use the current here, take away the current here, will give you the current here, because these two currents add up to this one here. And then use R equals V over I, we'll know the current and the voltage, and therefore we can find the resistance. So some students use that technique, and that's more than good enough to get to the answer as well. Now, part D. State and explain the effect on the output PD of increasing the temperature of the thermistor. So a thermistor, as we increase the temperature across the thermistor, that's going to reduce the resistance here. That's going to reduce the overall resistance in the parallel section, and the proportion of the overall resistance compared to the whole circuit will be reduced here as well. And therefore, the output voltage will be reduced as well. Okay, so we're referring to this here. So first of all, increase in temperature reduces the resistance across the thermistor. The parallel arrangement, therefore, the resistance drops. The proportion of resistance compared to the overall resistance drops, and the voltage output here will drop as a result as well. And all I've done is I've put that into words here.